house. My expectation is as the evening goes by, it's going to fill up even more. I encourage all of you to get your orders in for dinner. There's also special drinks they've made for this evening. So on this are the special drinks, which if you invert the order spell cafe quite nicely. But they're cosmoniums. Maybe Greg Huber can describe the drinks, but maybe not. But there are 4 different special drinks they're willing to make for you this evening, which will enhance the science input from the talk. So the idea of these is for our postdoctoral fellows at the Institute. These are scientists who've received their PhD and come here at the KITP for typically 3 years doing research. They're pretty much free to do what they want research-wise, and we ask them to do very little in terms of teaching or outreach, but some of them step up above and beyond, and Chuck-Hou is going to do that for you this evening. And we hope to do 4 or 5 of these, or maybe 2 or 3 per year. It depends on our availability of talent like Chuck. And so I do hope all of you keep coming. There are sign-up sheets if you haven't signed up for this to be on the mailing list. There's a piece of paper, I think, on all the tables. And I also wanted to introduce Greg Huber. So Greg, can you please stand up? I want to introduce Greg Huber, who's the Deputy Director at KITP and the head of our outreach program. And this has been Greg's effort to pull all of this together. So before we even begin, let's all give Greg a big round of applause. So at the KITP, we have about 1,000 visitors per year who come here for long periods of stays, typically a month. About half of them are from outside the US. So most of our people at the Institute are only here temporarily, but we do have 5 individuals who have a special title called permanent member, as opposed to visiting member, and one of those is Leon Balance, who's also a faculty member in the physics department at UC Santa Barbara. And so with no further ado, I'm going to hand the mic over to Leon, who's going to do the introductions.
Okay, thanks, Lars. It's fun to see this group here. I think we're going to have fun tonight. Lars already covered a few of the things I was going to say, so I can skip a few things. I want to tell you a few bits of information. The cosmoniums, which Greg and I sort of inspired with the help of the SoHo staff. Their takes on cosmopolitans, but cosmonium actually is a fictitious element that featured in an episode of Lost in Space. I don't know how many of you have seen Lost in Space. I'm at the age where I watch it. Maybe not everyone is. Anyway, so you can enjoy a little nostalgia and hopefully enjoy the drinks as well. Please enjoy not only those drinks, but whatever suits your fancy, and some food as well. And tip your servers plenty to let them know you're enjoying the event. Let me move on to the, I'm supposed to mention something else. So we're kind of a newcomer here as a KITP to this particular type of science outreach in a kind of pub club venue, but there's an older kid on the block, which is the Santa Barbara Museum of Natural History. They've been running a science pub for quite a few years, and I'd like to tell you that they're having an event in a couple of weeks on the 28th. Their science pub is held at Dargan's, and they'll be talking about scientific photography. They have a presentation on going beyond the Kodak moment. Scientific imaging zooms in. I think you'll find it very interesting, and I'll pass this around for people to look at in case they're interested. Okay, so for today's main event, you'll be hearing about future stuff. This is something kind of dear to my heart. So I don't know how many people of you have some idea in your head when you think about theoretical physics. I guess you've probably had some idea since you came here. How many people think physics is interesting? Yeah, good for you. So, I do. So most people, if they have some idea of what theoretical physics is, they think it's kind of study of extremes. They think either theoretical physicists are studying ephemeral, tiny submicroscopic particles that might live for an unimaginably brief time, created in almost an instant in a super high energy particle accelerator somewhere in Switzerland. Or they might think of physicists studying the biggest phenomena in outer space, the formation of galaxies, or the bizarre environment at the horizon of a black hole. But physicists, we have certain conceits. Physics is actually, what most of us believe as physicists, physics is a theory of everything. And physicists are not known for their modesty. So there's a lot of stuff between black hole horizons and the Higgs boson. So physics not only describes these really exotic objects, but it describes matter that you can hold in your hand, like this piece of paper, or everything around us. So our speaker today is going to introduce you to this, to what is extraordinary physics of ordinary stuff. And how theoretical physicists are working to create new materials that might be anything but ordinary. Chuck-Hou, sitting right here, he's a theoretical physicist, a postdoc working at the Café Institute. He got his bachelor's degree from Caltech, and then went on to graduate school for a little while at UC San Diego, and then at Rutgers, where he got his PhD a couple of years ago. Since then, he's been working as a postdoctoral fellow at the Café Institute. Chuck is, I would say he's a bit of a cyborg. He combines scientific acumen and a great deal of personal charm, as you'll see, with a virtuosity with computers. He puts those things together to do research on the cutting edge of numerical simulations of new materials. So let's give a hand to Chuck and let him tell you about
Thank you, Leon. That was a really nice introduction. And again, I want to thank Greg, because Greg put a lot of work into putting this whole event together. So thank you, Greg. Okay, so my talk is called Future Stuff, Unearthing Secrets of the Periodic Table. And I've started with a picture of the British Library in London. And there's a reason I stuck that up there. It's going to be also my last slide. I'll come back to it. Okay, so this is what Leon alluded to. What is the complexity frontier? So as theoretical physicists, in the public eye, we usually think of things on a very large scale. So things like galaxies, black holes, the entire universe, or things on an incredibly small scale, quarks, atoms, subatomic particles as well. And what I've plotted the horizontal axis is length scales going from the very small all the way to the very big. And the complexity frontier I want to talk about is not at either ends, but in the middle. What happens when you start putting many, many atoms together? Things get really complex really fast. That's the complexity theory, and that's the topic of this physics talk today. So this talk is about the periodic table, and then how we build off the periodic table to create new materials and future stuff that we haven't seen today. So in order to understand the future, we want to spend a moment to look back into the past and understand where we came from. So this is, maybe a long time ago where we came from, a couple million years ago, 1.9 million years ago, 243,000 years ago, an early human. And humans started by using rocks and flint and being able to create tools. So this is the Stone Age. And then we progressed to metallurgy and understanding that you could harness fire and various elements to create copper materials. Bronze, this is bronze, which is a alloy of copper and tin. And then iron. Oh, is this a problem? It seems like when I turn my head to the right. Yeah. Okay, so I need to just stand like this. Okay. So I'm going to flash up the periodic table, and hopefully you remember this from chemistry class or physics class in high school. 5 years ago, 10 years ago, 20 years ago, whenever it is you guys were there. And what I've shaded in are the elements which are known at the time period that I've plotted in the upper left. So this is 3000 BC, 4 millennia ago. And there are really only 4 elements which are known in antiquity: copper, gold, carbon, and sulfur. By the way, this thing is called the periodic table currently because there's a periodic structure. There's a structure to these compounds as you organize them. So as we go from top to bottom, we're going in increasing atomic number, so that's increasing number of electrons in each atom. And they're organized in vertical columns as well, because each group of elements in the vertical column have similar properties. So it turns out, for example, carbon and silicon and germanium have similar properties in a certain chemical sense. So let's take a journey through time. So this is 3000 BC. So let's jump all the way to 1 BC. So we've seen that humanity has discovered some more materials, some more compounds. For example, in addition to copper, we have tin, and copper and tin put together gives you bronze. So that allowed the humans to create bronze, which ushered in the Bronze Age. Iron, that's another material. That was discovered not too long ago, probably about 1,000 years ago or less. And with iron, you can create metal instruments, which are so much stronger, so much more durable than bronze. So literally, you could cut through a bronze shield with iron. So this is why people developed increasingly. So let's just scan through history. We're going to jump all the way to the Middle Ages, 1600 AD. More elements. Not much happens. And then suddenly around 1800, chemists and scientists were able to begin isolating materials at an increasingly fast rate. Actually, at about 1 per year. So every year, a new element will be found. And so we're going to slow down and jump by factors of decades. So here's 1810, 1820, 1830, 40, 50, 60, 69. I'm going to stop right here, because this is when the modern periodic table first took form. But I think you guys will recognize a lot of the elements here, right? There's carbon, there's nitrogen, there's oxygen, that's what we breathe. Sulfur gives you this very horrible smell when you pass things out the other end of your body. There's all sorts of materials which you hopefully are familiar with. So who put this table together? Yes, Mendeleev. You got to remember that we are looking at this with such incredible hindsight. We understand quantum mechanics. Quantum mechanics is the theory, the microscopic theory that allows us to understand atoms and understand how electrons and protons and nuclei are combined together to form atoms. But he didn't understand it. He didn't even understand that there were electrons or neutrons at that point. So it was just a collection of materials, a collection of elements. And this is Mendeleev. He was born in Siberia, in Russia. He had a very hard life, actually. But this is the first periodic table that was written down way back in 1869. And you see it looks very different from the periodic table that we see today, actually because it's turned on its side. So let me go back a little bit. For example, you can recognize here there's boron, carbon, nitrogen, oxygen. And you see right here already, there's boron, carbon, nitrogen, oxygen, and so on. So he had the right idea. He was able to organize these disparate elements into a periodic structure. And the incredible thing with science is that you have hypothesis, you have a theory, so you need to be able to make predictions from it. So what he predicted was that if the elements, in fact, followed this periodic law, there should be there was some missing. So I'm going to highlight them in red. This one right here, this one right here, and this one right here. There are 3 elements. There are holes in this periodic table. He thought, these must exist. And it turns out, this here is gallium, this is germanium, and this is scandium. And these were all discovered in the next 30 years. And so this gave remarkable proof to his idea that indeed, using this idea of a periodic table to organize the elements was the right way to go. So here we are in modern day. I filled in the rest of it. And these are all the elements governed by quantum mechanics. These are probably all the elements that will exist or ever will exist. The ones at the very bottom are actually a little unstable, so these decay radioactively. But this is what everything in our world, all the materials that you see around us, is made of. So that brings us a journey in time all the way to current day. So what is this complexity frontier that I was talking about? Seems like we've organized things pretty well, right? Oh, before I go on to that, I want to say that yes, atoms do exist, and we do manipulate them every day as physicists. This is a picture taken by a scanning tunneling microscope by a friend of mine named Dina at Argonne Laboratory. These are images of graphene, which is composed of carbon. So these are actually graphene. These are actually carbon atoms. Right here, 1, 2, 3. You can see them. You can see them, and you can manipulate them with a STM tip. So atoms are very, very real, and we use them every day. So where is this complexity frontier? So complexity lurks behind the behavior of many, many particles. So when we have a piece of material, we don't have just one element, one atom of carbon or oxygen or whatever it is. There are many, many, many of them all put together. So here's an iPhone, and you want to take a gander at just how many atoms are in this iPhone. The answer is about that many. So, and there's a lot of zeros in there. 10 to the 23rd, 100 billion trillion. So you can imagine putting together that many carbon, iron, whatever atoms, the behavior of the conglomerate may be very different from the behavior of one atom by itself. And this is the idea of emergence, which I mentioned in abstract. That novel properties emerge from the collective behavior of trillions of particles. So let me stop and show you a small movie which I rather like. Let me see if this counts. I want to illustrate the idea of emergence, that the properties of many particles is not necessarily the properties of a single particle by itself. So this is a video taken at the Bristol Motor Speedway in Tennessee. I don't know if you guys have been there, but I didn't take this, but this is from YouTube. And this is a video of people doing the wave. So I'm just going to play this. I don't think there's much sound. Here we go. So you can watch. So here's not 100 billion trillion, but this is 130,000 people. And so what do you see? Well, each person has 2 arms, 2 legs, a head. Maybe they have clothes on. Maybe they have a beer on them. But they can come together and create collective phenomena, which is just so different from a single person. A single person does not look like a wave moving through the crowd, right? I mean, this thing has a speed. It goes in a particular speed. It has a width. I'm just going to let it play for a little bit because it's just really cool. You know what? I think they were trying to break the Guinness World Record at this point. And so they had to go around at least once for it to count. And I think for most people doing the wave simultaneously. It's a little hard to see, but you can see the wave coming on. Yeah. So hopefully this impresses upon you the idea that the behavior of a collection of many particles is not necessarily like the collection of the behavior of a single particle by itself. We'll let it come around. Okay, we'll let it come around one more time. It's just so good. Okay, let's go back to my presentation. So that's the idea of emergence. Where's the complexity frontier? That we have the periodic table, yes, but when we put billions and trillions of iron atoms together, that they behave very differently than a single iron atom by itself. So that's one part of the complexity frontier. But there's another one, and that is how many different compounds exist. So you know the periodic table, as I've shown, has on the order about 100 elements. that's not nearly enough to explain the diversity of materials that we see around us. There's certainly more than 100 different materials. So where does that diversity come from? And the answer is that it comes from how we put elements together. So let's do it. And here's the question, how many compounds exist? Let's do a rough back of the envelope calculation. There's about 100 elements in the periodic table. So how many possible combinations can you make by combining two elements together? 100 times 99, or I'm going to make it extremely rough and just say 100 times 100 on average, right? So that's 10,000 binary compounds that exist. And the answer, it's not too far off. What about compounds which have three elements put together? 100 times 99 times 98, right? Or about 100 times 100. That's 1 million possible compounds. And we can keep going. How many compounds have 4 elements, right? So that's 100 million. That's a lot. We can just keep going and going and going. So this is a different complexity frontier that, in addition to having tons of atoms put together in a single chunk of material, that there are so many different combinatorial possibilities of materials that we can make. So how are we going to explore this vast space of all possible compounds? So when I put this chart up because I like to imagine throwing all the possible compounds, known and unknown, onto the map of the United States, and imagining that, as physicists, we're explorers. We're sitting on this complexity frontier and we're wondering just how far in this space of millions of possible compounds have we explored, and how are we going to go about doing that? So I'm going to answer this question in the second half of my talk. Okay, one way to do it is the way that we've done it for many thousands of years, and that's experimentally, right? So here's a picture of a bunch of powders, and my friends do this. They have a lab, they have various compounds, and they put them all together, grind them up, seal them in a quartz tube. This is a quartz furnace in the lower right-hand corner. And they heat it up, and they see what comes out. So this is one way of synthesizing compounds, experimentally. And this takes a long time, lots of trial and error, lots of work. And for all these compounds are dangerous, like selenium, which was used in a class of superconductors which were discovered recently. Selenium is very hazardous, and it's hard to work with these things. You have to be very careful, and it's slow and meticulous process. Option 2, we're theoretical physicists, right? So how about let's use computers to understand and compute the properties of materials. So let me take you through one compute cycle, what that kind of looks like, on a very grand scale. So here's a compound I'm interested in. It's called vanadium oxide. 2 parts vanadium, 3 parts oxygen. And this is an input file that I took a screenshot off my computer. You can see that it says vanadium has 23 electrons in it, and oxygen has 8 electrons. And these are the coordinates of where they should sit in the lattice. And so you visualize what that lattice looks like. Here's a picture of vanadium oxide. And remember this, because we're going to come back to this compound over and over again for the rest of this talk. So vanadium is in the gray, and oxygen is in the red, and I've drawn little bonds between them to give you an idea of how they're connected. So what we do is we put this input, along with algorithms, advanced algorithms which we developed, into a supercomputer. This one happens to be called NERSC, which is funded by the Department of Energy. And we put in to this computer, we need to program the laws of quantum mechanics. The laws of quantum mechanics, not just of one atom, but of many, many atoms put together. And hopefully that spits out a result. It tells us about the properties of the material. Is it a metal or is it an insulator? Meaning, does it conduct electricity? What about its thermal properties? Does it conduct heat or not? What about its optical properties? What color does it look like? Is it going to reflect ultraviolet light or not? So on and so forth. What are its structural properties? When you apply an electric voltage across it, will it change its shape? Those are called piezoelectrics. So there's tons of properties that we can compute using this cycle. Whoops, excuse me. So this is the compute cycle for one single compound. You can imagine doing this for tens of compounds, hundreds, thousands, just going through it, just computing properties of compound after compound. So this is one way to explore that frontier, that world of thousands of materials. So let me give you some examples of what are some of these cutting-edge materials look like. So we're talking about future materials. Well, this one is not so future. This one already exists. On the left-hand side is the crystal structure of hafnium oxide. So it's made of 1 part hafnium and 2 parts oxygen. And the reason it's so important is that it's actually in every single one of your computers. And let me take you into, it's like imagine that you zoomed all the way into a CPU and zoomed all the way in beyond the CPU down to the level of a single transistor. You're on the nanometer scale. And inside this transistor, inside these CPUs, are tiny nanoscopic wires which run electricity and do the actual computation that we see today. When we start miniaturizing, making these things smaller and smaller and smaller, it means that the wires come closer and closer and closer. So you better have really good insulators between them. Insulators which can be only a couple of nanometers thick and still be perfectly insulating. Otherwise, your electric current is just going to leak between the wires, right? So Intel was running up against this problem back in 2007. They realized that the dielectric insulator that they used, silicon dioxide, was just not going to cut it once you made it that small. And so they spent a lot of work, a lot of effort trying to come up with a replacement. And what they found was that hafnium oxide was a material which was incredibly insulating even when you made it extremely thin. So this is an example. So all modern day transistors have hafnium oxide inside them. So here's an example of a cutting edge material. Here's a material and an application which is we're looking into the future. So it turns out the military is very interested in vanadium oxide, a compound that I was talking about before, because it has an interesting property. If you change the temperature of vanadium oxide just by a couple degrees, it will switch between being a metal and an insulator. So why is that really useful for the military? Well, okay, so you want your jets to be stealth jets, and you don't want them to reflect radar. And radar, electromagnetic waves, reflect off of metallic surfaces. So you can make the entire jet out of insulators, then it just wouldn't reflect radar, and you wouldn't be able to see it, right? But there's a problem. There's a problem with that. Because then you cannot transmit, see an antenna is made of metal, so you can never communicate with anybody on the outside, right? Because the whole thing would be insulated. So the idea was, let's make an antenna out of vanadium oxide or some other comparable compound which can switch on the femtosecond time scale between the metal and insulator, so that you can just turn on, transmit the signal that you wanted, and then turn off again. So that's an idea, that's an application. I don't know if it's seen the light of day yet, but I'm sure the military is pursuing various ideas that are top secret and I don't know anything about. So here are two cutting edge materials. The reason I put this up, I want to go back a little bit to this slide on the left-hand side. It's kind of funny, right? We've used computers to understand material. First, had to master materials, the silicon technology to create computers. And then we used computers to understand more materials so that we could make computers better. So sort of bootstrapping, recursive loop. And so I like this picture here. This is from Peter Engel's Holding the Universe. I used to love origami. And this book has some of the most difficult origami pieces that I've ever seen. A butterfly with 6 legs, 2 eyes, a head, a proboscis, wings. I mean, it's incredible. And this is his front cover. It's showing an origami pattern which is folding itself. So that's the idea I want to come across. That, you know, as technology progresses, we can build upon itself to advance further and further and further. Okay, so I've taken you through the compute cycle. We can take a material or a lattice that we're interested in and figure out what its properties are. But let's say we've done this for hundreds or thousands of compounds. The number of compounds is more than about 100, which is what one man could write down on a piece of paper. There's certainly no way that we can do this with hundreds, thousands, tens of thousands, millions of compounds. We're going to have to find a way to organize them that's beyond what we can do on a single piece of paper. So the idea here is going back to emergence, that, you know, in fact, all these materials are not like individual, special, different from everything else. They're actually common trends that connect different materials together. And if we're able to identify what those trends, those organizing principles, those emergent properties, then we can start organizing this vast space, this huge database of materials that we've computed properties for. So here's a concrete example, going back to vanadium oxide again. So this is a phase diagram, and scientists love to plot this stuff. So on the vertical axis, I have by a different atom. So on this side, let's start replacing vanadium with chromium to eventually form chromium oxide, which is a different compound. On this side, let's go and replace those vanadium atoms with titanium. And that forms titanium oxide. Titanium oxide, I think, should be, oh, titanium white's actually a different compound. Titanium O2, which is different from titanium 2O3. Anyway, I was hoping to make contact with titanium white, which is what you use to color white things. Yeah, white things, so many things in food. Actually, I was just eating some peach, these little peach gummies, and they use titanium white to color them white. It's kind of interesting. Now, directly to a gas. There's no intervening liquid phase. So this is a phase diagram for water. And hopefully you can see that there's some similarities between the two. So what I'm going to do is flip that phase diagram on the left-hand side by 90 degrees. Turn it this way. Okay, so now we have a solid phase, which is ordered, a crystal on the very bottom. We also have a solid phase, which I'll talk to a little bit, but a magnetic phase down here. There's a liquid phase over here, which looks like the paramagnetic, the insulator. And then there's a gaseous phase on the right-hand side, which turns out it's a metal. And it turns out that the analogy between these two is actually quite complete. That the electrons in these compounds, in vanadium oxide and actually many other compounds, behave just like this. That you can use the ideas of water, the organizing principles of water, to understand the organizing principles of how electrons behave when you tweak this set of materials. So here's an example of an emergent property. These materials don't behave like single electrons by themselves. No, they behave like metals and insulators and magnets, right? Those already have gone one level of complexity. And then on top of that, we can say, well, vanadium oxide sits here on this phase diagram. Titanium oxide sits over here on this phase diagram. And chromium oxide sits over there. And you can start imagining taking these little roadmaps and starting to build a bigger picture of the phase space, the space of all possible compounds that exist. So I just made it smaller. You know, maybe this is the correct roadmap for this several hundred compounds that sit over here. And here's another phase diagram. This is for copper. It's pretty simple because copper turns out to be a pretty boring metal. And let's say, you know, this will allow you to fill in this part of the possibilities of materials. And here's another phase diagram, a very famous one that's very near and dear to my heart. That is the phase diagram for the high temperature superconductors, which I'm not going to explain, but you can imagine filling in sort of piecemeal, feeling your way around this vast space, this vast complexity frontier. So this is what we're doing. One of the thrusts of physics that we're pursuing here at the Cochrane Institute for Theoretical Physics. Yeah. Okay, so I want to end. I think I'm pretty much out of time. No? I have to go for another. Encore. I guess I've only gone for about 20 minutes, right? Yeah. Well, I can talk about lots of things, and there's a lot of detail in this slide that I skipped over, which you can certainly ask me questions about. But what I do want to do is give you a picture of what may lie ahead. So this is a picture of the British Library in London, and it's just a beautiful library to go inside. And so something that we can look forward to in the future. If our algorithms get so good and our understanding of this space of materials gets so good, we may be in the future be able to say, I want a material which does this. I want a material which will have this color. I want a material which will conduct heat at this rate. I want a material which is insulating or metallic. I want a material which has these mechanical properties. Very stiff, or very flexible, or very hard, whatever it is. And you can go into your supercomputer and run the code and be able to and the computer will spit out and say, okay, here are the set of materials which fit your criteria. Go make them and see if they have indeed the predicted properties that we have, that the algorithms have predicted. So that's one. And the second one is, hopefully at some point, we'll have explored this space of materials so that we have a pretty complete map, a map of all possible, at least simple compounds that exist. And that's why I put up a picture of a library. Maybe looking back, 10, 100 years, 1,000 years from now, we'll see that the periodic table of all possible elements that exist was written down in 1869. And then, looking back a million years from now, maybe not that far, 1,000 years from now, we'll have all the compounds that exist that have been discovered and cataloged into the library. Thank you very much.
Okay, thanks, Chuck. So now we move on to the discussion part of the program here, and I hope we'll have a lot of input from all the audience. So please, would you? Yeah.
So if the periodic
let me hand you the mic so everyone can participate.
If the periodic table is the alphabet and
Yes.
vanadium oxide represents one book in the library,
Maybe
how
one
long
word.
did it?
One word. Maybe one word, yeah.
Maybe one word. How long did it take the supercomputer to spit out the results of what vanadium oxide was?
Well, vanadium oxide is a particularly challenging example, and let me go back to that. On modern day computers, for a particular temperature, a particular pressure, a particular lattice configuration, the simulation will take, if I got all the parameters right, I don't know, about a day. It's about a day. But there's a lot of trial and error to figure out what are the right, there's a lot of work we have to do to make sure that the code is running correctly, that we have all the laws of quantum mechanics put in the right way, that we accommodate for all the effects that are important, and to be able to do that. There's another set of compounds, so I haven't really talked about this, but there are a vastly larger group of compounds called uncorrelated materials. I can't really get into that, but what I do want to say is that for those compounds, it's extremely easy for you to compute its properties. For example, things like just elemental copper, things like that, you can do it, I can literally do it on my laptop in less than 10 minutes and get the properties of the electrons from it. It's extremely fast. And so there is a actually it's going off of that. This is okay, this is something I can tell you a little bit about. This is called the Materials Genome Initiative. And it's a fancy name, but it's the right idea that the White House put out. It's a funding call. And what they want to do is to be able to build this genome. They're using an analogy with biology, right? DNA is the blueprint of life. The genome tells us a lot about the organism. And so here's the same idea. Let's make a genome for all possible materials and be able to extrapolate and understand possible materials from there. And so there's several groups that are funded by this, and they're sitting there and scanning through all possible compounds. I think they've done the phase diagrams of all binary compounds, so all compounds with two elements in it. They've done it already. Whether they're correct or not, that remains to be seen, but they've been able to do it. And as of 6 months ago, they were still scanning the phase diagrams for ternary materials, so compounds with three elements in it. At some point, it'll be done, and probably refined and better and better.
Okay,
So assuming you can put these together to create a new element or complex, what do you see as the future for my programming my 3D printer into putting something in that will have conductivity and a certain hardness or softness or flexibility in different parts of it, so I come out with a part that is based upon the formulas of the different elements that you're talking about that theoretically can be put together once we figure out how they can fit together?
There certainly is a possibility, but there's a huge challenge there. There's a huge challenge there, and that is of length scales. So our printers, 3D printers nowadays, operate on sort of millimeter or fractions of a centimeter length scale, and they use glue to glue these little tiny particulates together. If you truly want to build a material atom by atom, so you're talking about creating a transistor, or you're creating something where you're truly putting atom by atom together, that's going to be much, much, much further in the future, because that involves a manipulation and understanding of length scales that are so much smaller than what we can do on a 3D printer today. But that already exists actually at a very limited scale. 3D printers are amazing because they're cost effective, they're retail. And you can just go and buy these things for, I don't know, how much are they nowadays? Like a couple $100?
Yeah.
A couple $100, right? It's really impressive. 1,000? Leon has a printed, I think of a pyrocore structure, so a particular crystal lattice that he's very fond of in his office, which is made on a 3D printer. But going back to your question about can I create something that's going to be metallic or create something that has a particular fingerprint when you shine light on it and so forth, that can be done today, and that's using something called molecular beam epitaxy. So here, they literally have a vacuum chamber and a substrate, a flat, inert, metallic, or whatever substrate they want, so a surface. And they have, I guess you can call them guns, of materials. So lanthanum, copper, oxygen, not really oxygen, but oxygen is too volatile to do this with, iron, various compounds, and they heat them up, and they shoot these vaporized materials and can paint them layer by atomic layer and create any, pretty much any compound which would be stable. You can create it layer by layer, layer by layer. But this is very expensive, very slow, and certainly not commercialized. But if people are able to do that in the future, then yes, you could go in and program, okay, I want replicator, I want something that, I want this compound. And if they could do it fast enough and create a huge macroscopic chunk of it, yes, that would be possible.
Let me just comment on Chuck's answer here about the, so this MBE machine is kind of a one-dimensional version of your 3D printer. You can kind of make anything you want, but only in one direction. In the other direction, it does what nature wants. You can buy them now, but it costs about $1 million, unlike the $1,000 for your 3D printer. And you also probably need at least 1 or 2 graduate students full-time for working, so it's a little bit more expensive, limited technology. Okay, so I think there was a question over there. We have a lot of questions.
This is good. This is good. My presentation went short, so we could have lots of time for questions.
When you talked about compounds, you talked about binary and tertiary. How far can you go to make compounds, or is it unlimited?
Probably unlimited. Well, you're limited by the number of atoms or elements that exist in the periodic table. So you couldn't make a compound that is more than 100 different elements in it. But that would be a very complicated compound. I don't know what that would be like. But you could imagine that in the future that we have the nanotechnology to pattern compounds which have these incredibly complex structures with probably close to 100 elements. Who knows, right? But
so what is the maximum that most compounds have?
You mean nowadays, sort of realistically?
Yeah, nowadays.
Nowadays, we probably max out at 3 to 5.
Okay,
Yeah.
thank you.
3 to 5 elements. So, for example, these high temperature superconductors that I talk about, they're pretty complicated. And for example, it's bismuth, barium, calcium, copper, oxide. That's 5 different elements there.
How close does all this bring us toward the realization of the alchemical drain of transitions? And that was the way I would ask that, would be to say, can you explore with these computer programs the chemistry? Can you find ways to transition from one structure to another? Can the computer find pathways to move from one molecular structure to another?
Right now, it is possible, but in a very, very limited sense. So the question was, can you, I'm not actually sure if I understand your question completely. Do you want to take a compound with a particular crystal structure and then change it into a different structure?
Yeah. Can you do the chemistry? Can you figure out whether catalysis, whether you're going to have catalyst, or figure out a recipe to get from here to there?
It is possible, but very primitive at this point. Because you need to be, so in addition, so this is quote an easier problem. The one that I'm talking about right now is an easier problem because you have a lattice, the atoms are fixed in their position, they're not moving anywhere, right? Here you're talking about actually having atoms moving around freely and diffusing, moving according to electrical or chemical potentials and how they interact, right? So that is possible. They're orders of magnitude even more difficult than the problems that I've described here. So there are groups that work on this. They use molecular dynamics simulations, it's called, to simulate the pathways, reaction pathways of materials.
I wonder, you've been talking about combining elements. How many elements could there be you don't know about yet?
Okay, that's a good question. And it's the realm of nuclear physics, actually. So how many, can I go back to the periodic table? Oh, I wish I had a different chart for you guys. Because there's a chart. So what is it that tells you what is one element versus another? It's the number of protons or the number of electrons in that atom. So it turns out protons are positively charged, electrons are negatively charged, and you always have to have an equal number of protons and electrons in an atom. So what tells you one atom from another? That's the number of electrons or protons equivalently. Okay, so why can't we just start creating atoms with 1,000 protons and 1,000 electrons? Okay, that's your question, right?
I'm only asking, is it possible?
Is it possible? It turns out, no, it's not, because the nuclei become unstable. So when you start trying to cram so many protons and so many neutrons in a nucleus, it actually will start decaying. It won't like to stay together. And the exact details of this has to do with the weak force and the strong force. And I'm actually not an expert in this, so I can't say. Do you know anything more about this? There's an island of stability, which I've heard of. So there's a beautiful chart done by nuclear physicists of all the elements. But in addition to just this chart here, so for, I'm trying to think whether I want to get into this or not.
The black one's over here.
Just say no. No, it's interesting, right? It's really interesting. So it turns out that an atom is controlled by the number. What atom you have, what element you have is controlled by the number of protons, right? And the number of neutrons you stick in. Neutrons have no charge. They have no electrical charge, but they have another kind of charge. But anyway, you can change the number of neutrons in an atom without changing its character in terms of its atomic number, in terms of its valence, in terms of the number of electrons, right? And so here's a very simple example. I think you've heard of deuterium, right? It's a different isotope. So elements which are related by different numbers of neutrons are called isotopes. So hydrogen by itself has one proton and one electron, and that's it. But you could make a different isotope of the hydrogen atom, which has a single proton and a neutron in its nucleus, so two in its nucleus and an electron. That's called deuterium. You can also make something called tritium. Actually, this was very important in World War II because the Germans were trying very hard to create a fission bomb, and so they were using this thing. So it's called heavy. This is heavy forms of hydrogen, or they put it together with oxygen to form water, so heavy water. So there's a flexibility in how many neutrons you stick in the nuclei. So as you go to larger and more heavier elements, so for example, you get down to the bottom of the periodic table, it turns out that no matter how many neutrons you stick in, so I skipped over one little thing. It turns out that you can change how stable a nucleus is by changing the number of neutrons. So for example, if you have 50 protons, it might not be stable if you stick 50 neutrons in, but if you stick 51 or 52 or 53, that nucleus is stable. It won't decay, it won't radioactively decay and form these other elements. But it turns out as you go to heavier and heavier and heavier elements, you can't do that. It doesn't matter how many neutrons you put in, these nuclei will decay. So here's a long answer to your question, that no, it's very hard to make elements which are beyond what you see in the periodic table. The things on the very bottom of the periodic table already decay very quickly. And so
would the answer be about 10?
I don't know, how about pi? How how many more possible elements will be discovered over time? Unfortunately, I don't think something like unobtainium, which will be extremely. I don't think that's going to happen. Sorry, guys.
Chuck,
Yeah.
I heard about something that was a healing thing where you drink deuterized water. Have you ever heard of that?
I have not actually.
But it's what we're talking about with what they are doing in Germany.
Is that bad for you? Because is deuterium radioactive? It's not. No, I wouldn't recommend doing that.
Be expensive.
It would be extremely expensive, and I'm not sure how you would get a lot of deuterium.
Here, we're talking evolution here. Have the cutting edge scientists at all been thinking about the evolution of the human being, either with or without these elements? And I'm not talking about just a cyborg, but I mean like some kind of onward evolution of humanity, with or without these new elements.
I think we have enough of a playground. So there's something called the Inorganic Crystalline Database, or Inorganic Crystalline Structures Database. It's on my website. There's about 250,000 compounds, inorganic compounds that are listed there. There is another database which is maintained by the American Chemical Society, which has also, in addition to inorganic, also organic compounds. So compounds that are based on carbon. Things like benzene, things like alcohol, things like these complex. Oh, here's a really good example. I'm really glad that Greg brought this. Here's an example of an organic compound. This is a lipid. This is the molecule which forms the majority of the cell membrane that we have in our bodies, right? And it turns out that and what elements is this thing made of? Well, it turns out this is 1, 2, 3, 4, 5, I think, 5 or 6 elements. Pretty much carbon, oxygen, nitrogen, hydrogen, and phosphorus if you're going to do DNA, and sulfur if you're going to make amino acids. So with only 6 elements, that database, take plus or minus some, has 80 million compounds in it. So I think life, the complexity of life, when you're not straddled, constrained by the fact that you need to make a lattice of periodic repeating structures, if you're free to do whatever you want, that complexity frontier, those possibilities and combinatorics are so much bigger than the realm of crystals that I've restricted myself to here. And so already, now, today, 2014, we have 80 million compounds in that. Did I say? Yes, 80 million compounds in that database, and I'm sure we have many, many more to grow. That combinatorics is probably going to be larger than the number of atoms in the universe. I really haven't worked out the numbers, but my feeling is that it's just that big. So in terms of life, we don't even need to go and start building life based on silicon or based on germanium or whatever it is, right? With just carbon, I think we're going to be preoccupied for a very, very long time.
Okay, I think I've been neglecting the dark back.
The dark back corner.
What we call the cheap seats. Do you believe that there are unseen dimensions, and if there are unseen dimensions, would not those dimensions have their own periodic table?
Unseen dimensions. I don't know, when I take off my glasses, I can't see very clearly, so maybe there's unseen dimensions in that, maybe? Okay. It depends. Well, are you talking about parallel universes? You're not sure what you're talking about, so I guess I have the freedom to do whatever I want with that question. Yes, if indeed there were parallel universes, there's no reason why these parallel universes would have to obey the same laws that we have here. However, I don't think we'll ever. So there's this idea of multiple worlds, that they're parallel universes, that time is. Anyway, I'm not going to get into that, but. Why not? Because I don't know so much about it. And the other thing on top of that is, I don't think those theories of multiple universes have any testable predictions. Like, what would you test? Because in science, you need to make testable predictions, right? In order for the theory to be a scientific theory, you have to be able to take hypothesis and falsify, right? And so if there were other universes, that's great. But unless there's some way for that other universe to communicate with our universe, and for us to go over there and look, That question, unfortunately, doesn't really have an answer. And Chief O'Brien figured out a way to do it in Star Trek. That is true. I'm a strong believer in Star Trek. I watched it religiously, so did my sister. So clearly there are alternate universes with weird beings and
Star Trek, is that what she said? Oh.
Question here. I'm impressed with these neodymium magnets and how strong they are. It would seem to me that, I think that they're doped with, is it iron and boron? Or is that the kind of thing that you're talking about? You could take 3 elements and computationally model and then make stronger magnets?
So yes, there are groups, especially in Europe, they are specialists in this. They're able to compute the Hund's coupling. So they're able to compute the microscopic, and Leon's laughing because I'm throwing out physics. I threw out some physics jargon. They're able to compute the magnitude of those magnetic moments in the material and go from there and figure out if they can optimize.
Are we likely to see even stronger permanent magnets then in the future?
I don't see why not.
So they compute these and then they build them.
Please, you use the microphone.
Oh, the computer computes these properties, or that's C word. When you mix
compounds.
Yeah, compounds, and then they make them. Always make them.
Not necessarily.
But they're making the magnets, for instance.
For example, magnets, certainly, because there's a very important industry based around magnets, right? But, for example, I've created some fictitious materials on my computer, and I've run simulations for them, and I don't think they'll ever be made. If they're going to be made, I'll have to beg my experimental friends and give them a very good reason for why they should make this, because it takes a lot of work to make a single compound. So no, not everybody makes every single compound that we've done a calculation for. There are tons of compounds that we've done calculations for that haven't been synthesized. And there are many compounds that exist. Actually, if you go to some labs, there are these compounds that sit on the shelves, and you talk to them and say, well, I'm thinking of this compound with vanadium and oxygen and maybe some carbon and something, and say, oh, we made this 20 years ago, and they'll pull out a little while. It's kind of interesting. So sometimes the communities don't talk and are not as connected as they should be. So it goes both ways.
I'm thinking you're talking about all the compounds, but I'm wondering about a material that only has one material in it, like carbon.
Yes.
We have diamond,
Yes.
we have buckyballs,
Yes.
we have graphene. How are these things being put together? Are there artists putting them together? Are there craftsmen? Are there physicists? Will this be a 3D machine that will put these materials together in a way so they can be useful?
Well, I think that goes to what Leon was talking about, but that it's very difficult to control at this level how the atoms are assembled. I mean, we just spray down a layer of carbon, then we spray down a layer of oxygen, then we spray down a layer of neodymium, whatever, right? And hope that they arrange the structure that we're interested in. So we have control in this dimension, but we don't have control in the horizontal dimension. What you were talking about, different allotropes, so they're called allotropes. So when you take a single element and have just that pure element try to form a compound, put trillions and billions and trillions of them together, they can form different crystal structures. So carbon, for example, is the one that you brought up. There are different allotropes of carbon, different crystal structures. So there's graphene, which is just a 2-dimensional hexagonal lattice of carbon. There is diamond, which is what's called the diamond lattice. There's buckyballs. And what determines whether carbon forms one or other allotropes depends on the conditions in which the compound was grown. So and this is in the realm of material science and chemistry that I don't really understand. There's a lot of know-how, a lot of art to controlling, just when you change the temperature for how long, what oxygen pressure to put in that quartz tube at what time to get the compound that you want. So for that point, in that view, we don't have the ability to control every single little atom where we stick it yet. But hopefully we'll get there.
This is a point where physicists often have to rely on chemists, which
Yes.
we hate, but...
Some chemists.
So it's my assumption that the mathematical models are algorithms that are based on underlying physics, but then attempt to combine all of the possible combinations to predict properties. So my question is, how far along is the science and your algorithms to accurately and predictably predict the properties of the compounds you're hypothesizing?
And the answer strongly depends on the class of compounds that we're considering. So for regions of that map, for simple metals, simple insulators, things like silicon, things like copper, things like simple alloys and metals, those are very easy to do. And those are examples where I can literally do a computation in under an hour on my laptop and get the properties that I'm interested in to within the accuracy that I'm interested in. So for example, one question is just how spaced out are the atoms? So what's the lattice spacing between atoms, right? So you can compute that, and we can get, so maybe my short answer is that it depends on the degree. It depends on the degree. So you can get the lattice constant to within, probably a long time ago, to within 25%. That was really, really good back then. But now we want to get these lattice constants, the spacing between atoms, to within 1%. Right? So people are getting better and better and better. Okay, that's one example. Another example are, for example, being able to predict whether it's a metal or an insulator. There are some compounds where we predict that it's a metal, and it turns out when you go and make it, it's an insulator, right? And so here there are classes of compounds. They're called non-insulators or strongly correlated materials. Those are the buzzwords. That are very difficult to compute the properties of accurately. And so that's where the frontier we sit at today is. Developing algorithms to help us further our vistas, to help us explore these new classes of compounds, which we can synthesize some of them, and we can compute the properties for some of them, but we want to be able to do better. So the complexity frontier is pushed forward in many different ways. One way is just combinatorics, different compounds. Another way is how we arrange them together with lattice structure. Another way is just the properties, these strongly correlated materials that we don't really know how to compute the properties for, and we need to develop new algorithms and better supercomputers to be able to do that.
So what about the other side of this equation? We've got atomic bombs and nuclear bombs. We split uranium, I know. We split plutonium. We split cobalt. What other bombs might we split meddling around with there?
You're asking me what other different types of nuclear fuels exist? Well, I'm not very familiar with making nuclear bombs. But what I can tell you is that in terms of nuclear reactors, in terms of nuclear fuels, it turns out that the couple that we have, uranium, plutonium, in particular those two, are the best. We've optimized it, so there aren't that many elements in the periodic table. And we've been able to figure out that these ones have the properties that we need. They fission in the right way. For example, in nuclear reactors, we need to be able to conduct heat away from, so we have a chunk of, so how do nuclear reactors work? You have a chunk of nuclear fuel, and it's radioactive, so it generates heat. And it generates so much heat that if you don't conduct heat away from this rod using water or whatever it is, this thing would melt, and then you would have a reactor meltdown, and that's horrible. This thing might explode, whatever, right? And the water that's conducting heat away is turned into steam, and that drives steam turbines. So it turns out that plutonium and uranium and some alloys of them, those are the best ones that we know of that conduct heat well and are stable and have enough radioactivity for us to generate power from them. So I don't know if, so I don't think there will be bombs which are made of, thorium or actinium or whatever it is. Do you have better information?
No, that's a good answer.
Yeah.
Thank you so much. How about, you're talking about fission.
Yeah.
How about, what is the progress made by fusion?